So hello, for today I will be giving a demo about Turing Machine Simulator with some built-in modules such as arithmetic operation and then copy, move, and then swap. Also some conditional operators such as greater than, less than, greater than or equal, not equal, and so on. So the test cases that I'll be using will be the square root of a number, test cases for square root of a number, and then test cases to search for the greatest common divisor between two numbers, and then a decrement, which I'll be explaining further, and then as well for increment, and then sorting three numbers. So I'll be starting first with the searching for square root of a number. So let's just dive into it and change the file to sqrt and then just run the Turing machine. And then these are the programs implemented for Turing machine, which start for SHR for shift right, constant one, shift right, copy, copy, shift left, multiply, and then shift right, copy. Then in here is if equal, and then go to 4 means you're gonna go back to step number 4, and then once it's finished, it will go to halt. So let's just go. Take for example, if we want to search for the square root of 4, we should be getting 2 as a result. And let's say we want to search for square root of 9, we should be getting 3 as a result. And oops, let me set the debug to false first so that we can see a clear one. So I repeat, so let's see, if it's 4, then we will get 2, and then if it's 9, we get 3. If it's 1, we'll get 1. And take note that the square root functionality in here is only for those numbers that are really perfect square. I mean to say, if it doesn't support the numbers that are not a perfect square. So other examples would be, let's say 25. So 1, 2, 3, 4, 5. This should give me 5 like this. So that's one example, one test case is for to check the square root of a number. So we can check also with searching for the greatest common divisor between two numbers. And these are the modules that it will run. And let's just dive into it. Let's change first the program name of a program file from sqrt to gcd, and then we'll just run it again. And then these are the program, and then one example would be the greatest common divisor between 2 and 4 is 2. Greatest common divisor between let's say 3 and 9, it should be 3, and then the greatest common divisor between, let's say, 5 and 3 should be 1. And it also works around if we put the larger number first. Let's say 6 and 2. 1, 2, 3, 4, 5, 6, and 2, which is has the greater common divisor of 2. And then let's say another one, 10 and 5. 1, 2, and then 5 should give us 5. So that's another example, another test cases that we can use to run for this Turing machine. And the next example is the decrement. So what this will do, given a number, let's say I'm gonna put I'll just put it here. Let's say I'm gonna put 1, 1, 1, 1 like this. So this should give me a result of a countdown. It's like a form of countdown. So starting from 1, 1, 1, 1, then 3, 2 until 1, and it should stop here. So let's take a look at that example, and let's change the file name from gcd to decrement. So let's try it out. Let's say 2, this should give us 2, 1. And then let's say 5, it should give me 5, 4, 3, 2, 1. Let's say I'm gonna put 10, should give me 10. So 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So this is another example that we can run in our Turing machine with modules that is used to print. It's like a loop to print like from n to 1 basically. And the other example is the counter example, which is for incrementing, which is the other way around. So given a number, let's say 4, this should give me an increment, a loop, kind of loop incrementing. So 1, 2, 3, 4, something like this. So let's change the file name into increment, and then let's try 3 first, and you can see 1, 2, 3. Let's try 6. You can see it's 1, 2, 3, 4, 5, 6. Let's try a bigger number, 10. This should give me until 10. So this is another example that we can use that you can run in the Turing machines with the modules inside it, with the purpose of printing an incrementing numbers. And the last example that I want to show is the sorting 3 numbers. So this is one possible one way that we can do to sort 3 numbers in the Turing machine. So I'm just gonna rename it real quick, sort 3 numbers. And when we run it, these are the programs. So let's say I have 2, 3, 1. It should give me 1, 2, 3. So the numbers, the 2, 3, 1 are being sorted. And let's say I have 1, 1, 1. It should just give me the same 1, 1, 1. And if I do, let's say 3, 1, 2, they should still sort it into 1 to 3. Other combinations, let's say 1, 3, 2 should give me same 1, 2, 3. And then the last one would be, let's say if it's, I'm not sure if I already give these as examples, but 3, 2, 1 should give me 1 to 3. So that's the demo that I have that to show how different kinds of examples, starting from square root, Brainstorm divisor, simulating a loops to increment and decrement until sorting, can be done using a Turing machine. So in here, I'll be giving a run through of the code. So the Turing machine I made is basically a class with some attributes. Self.q represent the states, and self.s represent the stimuli in the Turing machines, and the modules represents the existing modules in the Turing machine. And self.accept, this represents the accepting state and the rejecting state for each modules. And then self.confos, this is to integrate it with the conditional modules such as equal, greater than, less than. This will be used at that point. And for self input string, this is to store the input string. Pointer is to get each character of the input string. And self.debug is basically for me to debug. I'm gonna set it to true for now. And then just an example, if we set the self.debug to true, we can see a run through on how the strings are changing. So let's say let's get the simple one. Let's do the GCD. Yes, the GCD. Let's say we want to get the common divisor between 2 and 4. In here, we can see how the strings are changing from start to end. So we can see in here shift right. So shift right pointer goes to the right twice, and then copy to, it goes the same way. It shows the process, like which part of the string of the tape are being replaced by what, and how each pointer move, how each part of the tape is being manipulated, and for each step. So starting, and all of the modules in here represents what we have following the modules that we have set in here. So starting from the first until the end, kind of a long process there until the end in here. So I think this is the last few processes where we do, if I'm mistaken, move to one. Yeah, so we'll do change some part of the strings, and then can see the pointer is moving from going to the left and to the right over and over again until it reaches the final answer, which is 2. So to give a brief, to continue the run through of the program, the set input string is basically to set, when we first set the input string, the one that we type in the enter string in here, and then pointer would by default will be set to 0, and then this is just for the debugging purposes. For the initialized Turing, it will be all the states, the list of state, list of stimuli, and the accepting and rejecting state will be reset to 0 for every module's run. I will be explaining that further. And then for the parse command, this is what is being used to parse the command, basically to parse the input string. So if you can see in here, then actually might be better to look at the commands first before that. So you can see the commands in here are like a program for Turing machines composed of right and left, and then this is the transition, and then this is like replace 1 with X. Like when you see a 1, replace it with X, and then go to state 2. And then in here, when you see a sharp, replace it with sharp, goes to state 7, and so on and so forth. So these are the commands that are being parsed in here in the parsed function. So it will split it, and it will get the transitions and the memory part. The memory part is basically what we replace it with. And then the transitions is for you to go to the next state. Like when you, let's say when you see one, go to state 2, like for example earlier. And then in here, when you see one, replace it with X. And then this parse command, for each command, it will return the direction, left or right, the transitions, and then the memory, which is a list of list of tuple, if I'm mistaken. And then at state, basically adding the list of completing the details for each state, where each state should have a direction, each state should have an index, and then each state should have a next, which, let's say, like when you have 1, it will go to where? When you see a 1, it will go to which state? When you see is a 2, when you see is a sharp, it should go to this state. When you see is a X, for example, it should go to another state. And then memory is just another representation, the one that we parsed earlier into the state. We put it into the states where when you see a 1, then you replace it with what? See a 1, see an X, replace it with what? And then in here for each transitions, this is where we add the list of stimuli. And then for the memory, this is also where we add the list of memory. And then at the end, we just append this state into the list of all states. And when we process the commands, this is actually the commands that we have in here. Let's say for shift left, for example, commands will be passed into the process commands, and the process commands will be the ones to check if it's accept, then do this, or reject, then do this also. And then if it's not an accepting or a rejecting state, then you do usual you parse the commands which will return to you the direction, transition memory, and then you add state. And then next one is the run Turing. The run Turing is what running the command. I put the mult equals false as in here only for the purpose of this one, this part, because in multiplication, you will be running a move to one at the end of multiplication. You will be running move to one. So this is just to not show the string. So just when it's multiplication, just go through with it until the end. Like don't show the something like this, the move to one anymore, since it's part of the multiplication part. And the rest are pretty much the same. So if state the direction equals right, then increase the pointer to the right, else increase the pointer to one, and I set the self dot pointer into a variable instead, so I don't necessarily change anything. Although I did change it in here, but yeah, the point is just so I don't have to type along one self.idx self.pointer like a long time. So putting it into a single variable and then just manipulate it only here is pretty convenient for me. And then in here, we current is this for the current character, so it checks first if the current character is in the memory, then this is where we're doing the replacement of the string. So let's say this one where we actually this one we start with this string, and then at the end of this stage, at the end of this state, we end up with sharp sign being replaced by one. So that's one example of what is happening in here. And then the next state is basically getting the next state. And then this one is just for, again, just for debug. And this one is still getting only the index of the next state in the form of string, since I'm storing it in the form of string. And this one is getting the state itself, and then it checks if the direction is right, then do the same thing, and then direction is wrong, then do the other way. And then it will just keep on looping in here until it sees whether it accept or reject. So yeah, and then in here the self con true, self con false, this is usually made especially for this part where we use the equal sign. Yeah, where we use the equal sign, and then where we use the not equal, basically all conditional operations, where it will results to either true or false. That's what usually happens, and this is where we usually set self.con equals true, self.con equals false. But it doesn't mean that it will always be used in every part. Let's say copy doesn't have, like, they don't have any accepting or rejecting state per se. But yeah, it the self.con really will only be checked for the condition for modules that has conditional operators such as greater than, less than, and so on. And then this is where it does everything. So I kind of hard coded the all the modules that I have in here. So because I don't see any other way. So if it's in here, if it sees a SHR, let's say like this, and then it will just, this means that you should run the state self shift right, and then this is the parameter that you should pass into the self dot shift right function inside this Turing class. And then yeah, for basically for every keyword that we used in here, this is basically what it will do. And then the next, and then go to, and then halt in here basically means for the next in here, it will just go to the next state. So like shift right, go to the next, go to the next, like just keep it simple, go to the next, go to the next, like this. And then for go to, this is the states where it will jump. For example, in here, if EQ, it goes to 17. So it will not go here it will jump to state 17, shift left, move one, and then halt. So the go to basically simply means these are for the modules that involves jumping from one state to another instead of following the order that has been put in here. So yeah, and then the halt is basically the last state, which is to halt the Turing machine. And then the run modules basically says if it's halt, then stop it. Then if it next, then you're just going to check if len m len equals 3 equals 4. This is um to counter the different number of parameters, the different number of arguments that we pass, because as you can see in here, the next actually sometimes has one arguments to be passed, sometimes has two arguments to be passed, and sometimes don't have any arguments to be passed. So that's the purpose of this one. And underscoring here is just to extract the next, which we are not going to use anyway. And then idx plus 1 to go to the next module. And then the go-to part is this is where we just run it module x, like run the module and then put the arguments inside. And then this is where we're gonna check if self.con is indeed true or false. So the self.con in here will be changed from, like, for every modules it will be changed continuously, but it will only be checked in here. So it doesn't really matter if the values, like if it's not part of the conditional statement and then it changes the self.con, it still won't matter, because uh either way it will only be checked in here. Because when it's true, then it should go to another state, which is this x. This is the arguments I set to be the state. And then if it's false, then it will just go to the next state. Like in here, if this is false, then it just continue 12, 13, and so on and so forth. And then display string is basically just to display the string, and with the pointer, along with the pointer up here, down here. And then these are the modules that are available. And as you can see, there are a bunch of commands for each module. So it follows the same format actually. So for each modules, it will do initialize Turing first, which will reset the list of states, list of stimuli, and reset the accepting and rejecting state. And then the commands will be in the form of a list. And then this one is, there are some part of the commands that I can actually I can actually automate in a way, and then some other commands that I have to do it manually. So, and then self.process commands, this is where the q s well, the self.q, self.s, and then what else, self.q, self.s, and then self accept and reject will be initialize all the values for it, and then we run the Turing, which will give us the new string. And then I have almost forgot to mention this part right here. This is to remove the trailing sharps, because as you can see, some part in here, like for example, like I'm trying to look for a good example. Let's say this one, the part from here. I think this one is longer than the one in here. Yeah, it's one sharp longer. Yeah, but that's what happened. What I basically did in here is I uh split the string by the sharp, and then for for every string I just gonna put, let's say in here, plus, let's say, one sharp, or and then plus one sharp, for example, something like that. So that there will be no trailing sharps, so that, and because if I don't do that, it will fill up the whole thing. Yeah. And then the next part would be for each modules, the part in here is where I need to put extra sharp. Let's say for constants, because for constants, what it will do will be something like this. For, let's say, 1, what it will do is it will turned into, and the pointer, by the way, should be in here. Yeah, the pointer should be in here, and then what it will do, it will do something like this, and the pointer will go back in here. So as you can see, after this, there's an extra sharp in here. So I put 2 just in case, just to be safe, because either way it will be truncated anyways in the this part of the code. So for some part of the code, I put this when there's a possibility that it will extend to the right. So the rest of the code, shift left, it's just the same way, and then copy. And then especially for this one, I have to kind of take note um of the left and the right of the pointer, because it's a little important to see how many sharp should I make, because when you want to copy, you kind of have to check how many sharp you should make. And then yeah, for the commands, it will, some of them can be automated like this, some of them I just put it like this. And then yeah, and then for the move, it's the same thing. If k equals 0, meaning to say if it's move 1 0, it will just um delete, basically it will just delete the one, the existing 1 1 1s on the left. So let's say I'm in here and then I say move 1 0. What happens that all of these will be, I'm in here. Okay, I'm in here and I say delete 1 0. I'll let move 1 0. What happens is that all of these will be sharp. So it's like move move 1 0. And then aside from this, I have also the swap. Some commands just cannot be automated, so I have to do it manually, such as this one, and the rest as well, like this. Well, when I say that I cannot do it, that I cannot automate it, means all of the states, all of the transitions in the diagrams are actually different. It's not how you can say it, because sometimes, for let's say they're part of this states that can go multiple times. What I mean by that is they can appear multiple times in a row, they can appear consecutive in a row, depending on the value of j and k. That's why in here it's always for range of j or range of k, or k minus 1, j minus 1, because it always depends on the number of j and k. But as for the others, like swap, add, bonus means the subtraction, multiply, divide, and then greater than or equal. And then the rest of the comments, the rest of the commands are actually yeah, cannot be automated. So just code it manually in here for each module. So what happened is that every time it enters a new module, it creates another, somehow another instance of Turing machine. Like it always initialize the Turing machine again and again and again, so that it's a different Turing machines. Let's say if you say move to 1 and move 3 4, that's a uh different different commands, like different list of commands for move 1 0, move 2 1, move 3 4, for example. It's whole different commands for each of them. Yeah, but for those that don't really need command, then that doesn't matter. The go to state in here is just for me to print, like if go to is being executed only. And then from here, this is just the entering the program and stuff. So upon the part where uh, so the first function that's being run is always the add module, because the inputs are in the form of list of modules in the Turing machine. And then after that, it will run the from the add modules, it will run the other, like in here in the add module. This is where it will run all of these, like it will append all of the modules, and then from there After the add modules is done, usually I'm gonna set input string first. This is where, take note that when I do the add modules, the commands are not yet being processed. It's just setting up which functions to go to for these modules and so on. So, and then set input string is the beginning, of course, and then run modules. This is where all of it begins. This is where it begins. So basically the module X, module XY in here will call any of the functions that I put in here. And this function that I put in here will call also the run Turing function to do its stuffs. Yeah, so that's all for my demo. I hope it's clear enough. If you have any question, leave it in the comment section. Thank you.